Good evening. Yes, if you tried logging on after 9:30, you did see an error message coming up, can't resume. I think that was a carryover setting from last semester when I taught the course, and during that time, it was after March, and that's when the COVID started to really pick up, and we went directly as remote around that time in March. Yeah, this year, March. It seemed like working at home and staying at home, everything seems to be running together. But yes, chapter 7 is when it's first started doing online virtual quizzes, and I guess I missed the setting. So please try to log in and retake your quiz by today, please. Today we'll cover chapter 9. Let me start sharing my screen. Application. Share. Can you see my screen? I think yes, no?
Yes.
Yeah.
Thank you. Today is October 21st. It's quiz for chapter 7. Once again, if you had a hard time taking this afternoon, please after class log in and take it. We'll cover chapter 9 today. Chapter 8 we cover at the end of the course because I finally teaching this course. I find that one of the useless chapters in this semester because a lot of the code that you would see in there you would never write, you never get to look at, but it's just used for pure academics. So we'll go over that briefly, and then that quiz is also one quiz that will help boost up your quiz average because I literally will tell you everything that I'm looking for. But I'll go over it. So today we are going to go over chapter 9, which is pointers. After the lecture, I'll show you different ways of passing a variable now as a pointer. But last chapter, I kept on reiterating an array name with no braces is a memory address of the starting point of the array. This will come up again now. So we'll quickly go over the lecture slides, then I'll go to Visual Studio and show quick examples of the difference between pass by value and the two ways to pass by reference. In addition to that, I think that's about it. Yeah. If not, in the in-lab for this chapter, we are not going to carry on with the seed assignments, but I hope I still do, a lab that talks about pointers, and we'll just go over that to help reiterate pointers. So let's go ahead and get started. For those of you that have questions at any time in this slide, please speak up. Slideshow. Play for start. Once again, this chapter is covering pointers. Before we go on, a pointer is a data type that all it does is store an address of another variable. Let me repeat that. A pointer itself is a data type. It has an address, but inside that address stores an address of another variable. So which means changes to what the pointer is actually being changed to that value itself. So to reiterate, getting the address of a variable is simply just using the ampersand. Just like I did with pass by reference, I said this is your beacon. The ampersand is your beacon of Gondor, or if you like Lord of the Rings. If you see that you're dealing with reference, an address, something of that nature. So each variable in the program is stored at a unique address. Use the address operator to get the address of the variable. When you display this, you will get the address, and it's usually stored in hexadecimal. Pointer variables, often just called a pointer, it's a variable that holds an address. Because a pointer variable holds the address of another piece of data, it points to that data. So itself is a variable, but it just points to another variable. And once again, we have seen it indirectly. We have already worked with something similar to pointers when it comes to arrays. That's why I kept on reiterating the name of the array by itself with no brackets is an address. So it itself is like a pointer. It stores the starting point of the array. And this is what it just goes over and again. When you have this array, you are passing it in the address of the starting point of the array. And this is another way of saying we have also worked with another way of doing with pointers, reference variables. When you have this ampersand right here, you're dealing with the address. And anything that's done to this parameter is made changes to the actual variable itself, the actual argument. And notice the way it is here and how we call it. And we'll see the differences at the end of the lecture. Here it is right here. When you call jelly donuts, notice the ampersand here, but it's not here. When you call this as an argument, it knows to do the address. Any changes to donuts would actually be changed to jelly donuts here. You're dealing with the address, not the value. Pointer variables are yet another way of passing memory addresses to work with a piece of data. Pointers are more low level than arrays and reference variables. This means you are responsible for finding the address you want to store in the pointer and correctly using it. So what comes great power, it needs great responsibility because you can easily mess things up. To define a pointer, you use your data type, whatever the data type you want. It could be int, float, char, string, struct, class, anything, any data type that we have. Use the asterisk operator right here, and then the name of your variable. It doesn't matter where the spaces are, just make sure there's the asterisk right here. The asterisk is also used for multiplication. It's also used to define pointers. And later on, we'll find another use for this. So this has multiple purpose. So assigning the address to a pointer right here is you take this int pointer and then you give it the address of the number you want. The num right here stores address 04A00. But inside this int pointer right here actually stores this address. This pointer itself has a memory address of itself too, but because it has to have some place to store the value. But notice inside int pointer, it stores the address of this. Initialize pointers with a special value called null pointer. In C++, they introduced a null pointer. Keyword was introduced to represent the address 0. Address 0 is unusable. When I first started using pointers, I used them in linked lists in C. They didn't have the notion of null pointer. What we did instead of using address 0 is we would test it for a -1 value. If we gave a pointer, we would give it an address of -1. So we would always test with that. And now with version 11, they have this keyword of a null pointer, which has the address of 0. And so when you define something right here, remember for here, if you just hit int pointer, whatever's in memory at that location, if it's local, and you dereference it, could cause problems. So that's why now they're saying, oh, actually hit. That's why they says if you're not going to assign it right away, assign a null pointer so that way someone else or yourself doesn't dereference it and use that. But if you do it something like this, it's technically okay because you are creating that variable pointer, and on the next line, you are giving it value. Right here, here's an example, integer x. You create this as a null pointer, so right now, the null pointer, if you dereference it, is 0. You're taking the pointer and you're giving the address of x. So the value of x is 25. Notice nothing's changed from what we did before. The address of x is 0x7ee00. That would be the address of x. But this part right here is not useful. When you have a pointer, you want to actually get the value what the pointer is. So that is what we use the indirection operator, or dereferences a pointer. I call it the dereference operator. I don't like the term indirection operator, but technically the term is indirection. I like to use the word dereference because you have a pointer, you want to dereference it, what the value is. So take the reference, give me the dereference, to kind of get the opposite. It allows you to access the items that the pointer points to. In the previous example, if we use the dereference operator in pointer, we will no longer get the address that we did before. We would actually get the value 25. But it goes right. Again, you have end pointer right here. You assign 25. This right here is assigning a pointer to 0. On the very next line, you're wiping away that 0 and giving it the address of x. Remember, every time you run a program, you will get a different address. So when you do a cout right here, it's going to display 25. And then right here, it's taking whatever the pointer points to, dereference it. It will also display 25 here. Right now, it's saying take whatever I point to, that address, and assign it 100. So no longer is x 25, it is now 100. So the pointer itself and x, when you assign it to the address, are pointing to the same location in memory. So what you do to the pointer, you are actually doing to the variable itself. Here's a reiteration of the relation between arrays and pointers. When you right here display vals all by itself with no brackets, it displays the address. And when you do an individual subscript of it, you get 4. Nothing new here. This is all that we talked about in chapter 7. But now, you got vals, but now I take the val's name and dereference it. I get 4. Because the array name with no bracket is a memory address of the starting point of the array. So that means, hey, I have the address of 4 because that's a starting point, and I'm going to dereference it so it displays 4. So now I could use a pointer to say, val pointer itself, give me the address of vals, which is the memory address, and now give me, oops, I keep on hitting my mouse, val pointer angle with square brackets 1, which means, remember when you talk later on with increment decrement, it's not going to say go give me 5, but go down the size of the number of bytes of int, give me the next subscript, and that will be 7. And here's this example that we just talked about. Here's short numbers, and then they're just taking dereference numbers, and you get 10. Remember, array name by itself is a starting address of the starting point, so itself is a pointer. Now this is very good slide right here. Int vals 4, 7, 11, and then I have a pointer. Val pointer and vals now are both pointing to the starting point of the array. Remember, val pointer plus 1 goes down the number of bytes of how big that element is. If it's int, it's 4, double, it's 8. If it's structure, then it's how big the structure is going down. So that's what it says. Val pointer plus 1 times the size of an int. So this is what we call pointer arithmetic. So now if you take val pointer right here plus 1, it's going to say, hey, I have this. Ints are 4 bytes. So give me the address of 1 times 4, which would say go down 4 bytes, which gives me 7. And then dereference it. Notice this has to be in parentheses because unary operators supersedes binary operators. And it also helps for clarity. Because right here, this is unary, it would supersede. So we want to group this together and says, on this one, take val pointer, which points to right here, go down to, which would be 8 bytes. So that'd be 4. 4 would give me 7, go down 4 more, and that will give me 11. So this is what we call pointer arithmetic. It goes down to the size of that variable. Array names, val2, 17, pointer to that array, same notation, val pointer, angle bracket 2 is 17. Array name and subscript, so this is array, this is vals, the array name. Remember, array name, no square brackets, is the starting point of the array, plus 2 goes down to dereference it. And here's in the same way with val pointers, plus 2, dereference it, and give you 17. Different ways of coming out the locations in memory. Conversion from vals 1 is equivalent to vals plus 1. Doing this subscript that you would see in chapter 7 is equivalent to this. To me, this is a lot cleaner. I remember working my undergrad, the teacher wanted us to do it this way. I think he would be a jerk and make it more complex because we would just understand the concept of arrays and then we quickly went into pointers. Remember, no bounds checking performed on arrays, whether using an array name or pointers. So be careful. Here's just an example. They're doing num coins, giving it the array, and double pointer. Double pointer coins, remember, the pointer itself and the array, whatever you do, the pointer has to be the same data type of what it points to. Let me repeat that again. The data type of the array must be the same data type of what it will point to. Even though this is an array, both of them are doubles. So on line 15, coins itself right here is starting the point of the array. They're doing it right here using double pointer to, here are the values in the array. And here it is again using the other notation. This is using pointer notation as an array, and this is using it as a pointer. They are both doing the same thing. Different syntax, same thing. Be careful with increment and decrement. Int vals, angle brackets, 4, 7, 8, and this is your example. If you do with the pointer, vals plus plus will point to 7. Remember, it's not taking the value here for incrementing. You're dealing with pointer arithmetic. So it says, when I increment this, after this line executes, go down that number of bytes 1 times that number of bytes for an int, which would be 4. So that's why I point to 7. And this is the same way again. Take the address of val pointer, subtract 1 times the size of an int, which takes you back to 4. So this one will take you down here. Next one will take you back. We talked about this earlier, but val pointer plus 2 will give you 11. You start off right here. You go down to 1, 2, and dereference it. And this says points to 4. So this is just showing you different ways to go about your data, whether using array notation as a pointer or pointers. Just be familiar with how each work. Both doing the same thing. I don't care which one you use, but just be comfortable with how they work. And this is another example of what we just talked to using increment decrement. Initializing pointers. You can initialize at definition time. So you can say int number right here, and you can initialize it right away because I define my num first. So they can be on the same line, but this is defined first, num. Int val, array 3, and then I can do it. You can define at the same time. Note that they both have to be the same data type. Cannot mix data types. Here's an example, double cost, trying to work, it won't work. They have to be the same data type. Can test for an invalid address for a pointer with not PTR. Remember, if you assign it PTR to a null pointer, that address is 0. And remember, when it comes to 0, it's false. So when you not it, it becomes true. So remember, it's invalid data, and you not it, it's going to become, what it points to is going to say, yes, it is valid data. So what it is, it's saying, if I assign pointer to null pointer, and I want to test to see if it's an invalid address, I would want to not it. So because then that 0 turns to 1 and says, oh, yes, I am invalid, and vice versa. Be careful when you use pointers and what they point to. The first one compares the address, while the second one, statement with the dereference operator, points to what it points to. So be very careful on this. Whether you use the assignment operators, equality checks, less than, or equal to, and so forth, know what you're comparing. With no dereference operator, you're comparing addresses. With them, you're pointing to what they point to. So be cautious on that. Here's another way that we are going to be able to pass reference variables to a function, and I will specify this out after lecture today. Sometimes it's easier to see. When you see all 3 ways we can pass values. So, pointers as a functions. A pointer can be a parameter. Yes, it can. Works like reference variables to allow changes to the argument from within the function because we are passing the address. Requires an asterisk on the parameter in the prototype and in heading. The asterisk pointer in the dereference to the pointer and address as an argument to a function. I will specify this out so you can see it visually at the end of class. Well, let's do it right now. That's why I'll just do it right now. It's on your mind. So for pass by value, can everyone see that clearly? So small.
Oh, that's good.
Okay, thank you. Pass by value. This is a prototype. And I'll just keep with int. We have an int. With reference variables, as we know them now, we have pass by reference as int ampersand. Reference variables by pointers can be void passed by pointer. We have an int asterisk. If we have a variable named int x that we're going to pass along, when you do pass by value, you just pass with a simple x. With pass by reference, you do the same. X. With pass by pointer, you have an ampersand x. See the difference? Remember, this is a copy. This is going to pass in the address. And then this is also going to be passing in the address. Now with the function definition, void nice. Oh, I thought I was going to hang it. Pass by value, use integer I don't care. I'm using this because remember, this is a parameter, it's a placeholder, so it doesn't have to be the same. So for me to do anything with it, I don't care. I can assign this to 20. Assign this to 0. When this gets called, x does not change because it's passed by value. If I call this right now, void pass by reference integer x ampersand x whatever. I change whatever to 20. I don't like it to look like this. I like it to look like this. When this gets called, x is no longer 0. It's now 20. Any questions on that? Notice the difference. Pass by reference, still use x, but the beacon is this reference variable right here. Now when it's void passed by pointer, it's integer x. I don't care again. I don't care. This could be x. Let's do 3. Y. And I'm going to do y. Dereference that. I want to change this to 100. When this gets changed, I'd like it to be cleaner. X is no longer 20 now, it's 100. I want you to understand the difference between these and be able to know the difference. Both of these, pass by reference and pass by pointers, passes the variables addresses around, and what you do in that function is seen outside. Pass by value is not. Play with the current slide. That's this slide broken down with all the other ways we pass variables around. Here's an example of swapping values in an array. So if you want to swap things around, you would pass, remember when they did the arrays? If you pass individual elements array out, you need to use the address variables so they can swap. Whatever you values in x and num2, you pass the reference variables in, and then you can swap them. Here's an example of passing functions by prototypes. Int asterisk, in asterisk, you pass in the address right here, and notice with the pointers right here, you actually use the asterisk, just like I showed you a moment ago. This is where it starts to get confusing for students, is pointer to constants. This means what the pointer points to is a constant. If we want to store the address of a constant in a pointer, then we need a pointer to a constant. The pointer itself, let me make this clear, the pointer itself is not constant, which means I can change what I point to, but the address of what I point to, but I can't change the value of what I point to, if that makes sense. So when you have examples, suppose we have the following. This is constant, and then you have this array as constant. When you go through each one of these, you can't change the rates because that pointer, what it points to, is constant. So what they do is they put a constant right here. Be very careful right here. This is the pointer notation right here. If it's to the left, think of this as the assignment operator saying, whatever it points to, it's constant. But yet, I can change, when he did here, rates right here can move down. It can change what it points to, but it can't change the value. For example, in value 22, this pointer is not constant, but the value it points to is, which means I can later on say pointer equals assignment, the ampersand value 2, if there's a value 2. The pointer itself can change to where it points to, but it cannot change the value of what it points to. A pointer that points to a constant, a pointer that cannot point to anything except what it's pointing to. But I can move from the pointer pointing from student A to student B, but I can't change anything about student A. Did we miss one? The constant. Yes, this is the other one. Well, I must have missed it. A constant pointer, notice it's on the other side. In pointer, it doesn't have the constant over here, but the constant is on the right side of the asterisk, which means the value that the pointer points to can change, but the pointer address that it stores cannot be changed. Which means when I assign this address to value, I cannot change what my pointer points to. It's always going to point to value. But since the value itself is not constant, I can change 22 to make it 50. And this is when you want to use them both. A constant pointer to constant, which means what it points to cannot change, and the address of the pointer cannot change. So in other words, you're stuck. All this stuff before that we talked right now is things that you can do with pointers. I never did crazy stuff with pointers with arrays like you see right now, even though my undergrad instructor wanted to do us that crazy stuff. The whole point of pointers is dynamic allocation of memory, like a vector. What happens during runtime if I need to allocate more memory? In C and C++, you have operators such as malloc and calloc, which will go ask the operating system to give you more memory. And the way it does is it returns you a pointer to that memory location. That's, to me, is what pointers were defined for. Because when I do new or I do malloc or calloc and ask the operating system for memory, it's going to give me a memory address, whether it be invalid as -1 or 0, or it's going to give me a valid memory address that I can point to with a pointer. That is the point of pointers. All this other stuff is fringe benefits of pointers. So dynamic allocation of memory is during runtime asking the operating system for more memory. So when you use the new, in this case, it's asking, hey, operating system, I need 8 bytes because it doubles 8 bytes. And if it's able to give you that address, it's going to give you an address. And so that's the way pointers are useful, because now you have a pointer to that memory location. So now you can start storing stuff. That's the purpose of pointers. So for an example, this is kind of a bad example, but it still works. Can also use it to new allocate an array. So you can say, hey, how much memory I need? I need 25, size 25 ints. So new double size. From there, I have a pointer to the starting point of that memory address. And then I can iterate through it. For those students that will go on to the next course, you can start talking about linked lists, and linked list just points to something else, and then that's where addresses come in pointers, because now you're pointing to another location in memory. It might not be sequential like it is in arrays. So you would do another structure and you say, I want this structure to point to something else, and that is what pointers are used for. Always test if you do dynamic allocation memory, read the documentation on it to see what it returns if it does not give you the correct memory address. Whenever you declare memory, even though in private function calls, those variables will bye-bye when the function ends. But if that function does not end, please let the memory be reclaimed by using the delete operator. If you use the new, if you're done with the memory, use the delete operator to be reset back to the operating system. Java and other languages sometimes have garbage collections and so forth that look for unreferenced values and give them back, because you have limited resources, no matter how much RAM you have, connections to database and so forth. If you ask for a connection or ask for memory, always try to free it back up when need be. There's been a lot of examples where we would have an application run and we won't do anything. Even though those threads running to handle updates and so forth, sometimes we have noticed when we had the application run for a while and we didn't do anything, we would see the memory becoming bigger and bigger and bigger and bigger, because some of the processes happened but never freed up the memory, so it kept on growing bigger and bigger. So that was a nightmare to find. Use delete to free dynamic memory. Delete the pointer. Use the square brackets free to delete the dynamic array. Only use delete with dynamic memory. Here's an example. How many days of figures do you wish to process? The number of days. And they use a new doubles right here. Oops. This is a pointer to it. You're able to then iterate through, enter in all the values right here, calculate it back up, do all the calculations, and display the information. At the very end, they delete the array, and then they set the cells back to null pointer to that way. If anything else after this, it's now pointing to the unusable memory. Because if you don't do this, someone else after you might try to dereference that. So be careful. Pointers can be dangerous. You can, like with I mentioned before, local variables inside a function. Remember, those are the life cycle of that variable. Once that function ends, it goes bye-bye. It gets reclaimed. So you can return a memory address from a variable inside a function. Be careful, because a function should only return a pointer or an address when the data type that was passed to the function as an argument, which means if I want to return back that memory address, make sure I pass that argument in. Which means if I pass it in, that means when that function ends, the variable still exists. But if it's local and that the local variable is just there and not passed in, I can still get the address of the variable, but it's no longer pointing to that address anymore. So be careful. Or you dynamically allocate memory inside that function. That's another fine thing to do. Here they're taking in random numbers. Here's a pointer to array number right here, null pointer. If it's less than 0, return a null pointer. If not, they're doing all this stuff, and then later on returning the address. This is acceptable because it's not something that they passed in. They are dynamically allocating an array, which is fine. Even though they are passing it in based upon a number that gets passed in, it's dynamically allocated. Be familiar with this. You will not need to write programs on it, but just be familiar with it. In C++, you can use smart pointers to dynamically allocate memory and not worry about deleting the memory when you are finished. Someone came up with a smart notion because a lot of people were dynamically allocating memory and not freeing it back up. So now they create these smart pointers, unique, shared, and weak pointer, to help with memory management. To use these, you must use the preprocessor directive memory. And you can see this example, unique pointer, and so forth. Once it's done, the notion of int indicates a pointer can point to an int. Of course, the variable name is pointer. The expression is new, allocates a chunk of memory. So this is saying, take this pointer, allocate a new size of an int, and the reference operator is this. Here's an example, and then it displays the content. Any questions regarding pointers? Let me stop sharing. That was a more challenging chapter with having to do with pointers, but any other questions or concerns? No? Then I will leave any questions open up for anything else.
Yeah, I was wondering if I can get with you about the lab after all this.
Let me see. I don't see pictures. Who was this that needed help?
Michael.
Okay, yeah, I can help you.
And can John go after that?
Yes. We can do what we did before if you have questions.
Yes, sir.
So, any other person have questions about the class or labs except for Michael and John? If not, you guys are free to go. Please take your quiz. Now that I fixed the setting.